Right, so for the second exercise, let me first of all draw the diagram. Then we'll read the question as we are looking at the diagram. Okay, so let me first of all draw the diagram. Let me just add the new page like so, and let me draw the diagram. So this is about mouvement relative. So the repère absolu, I'm going to draw it in red. The reference frame, that is absolute, I'm going to draw it in red, like so, like so. So you have the X, Y, and Z axis. So this is the X axis, the X axis, then the Y axis, like so. And then we have then we have the reference frame that is moving. I'm going to draw it in black. So I'll draw it in black like so. So we have a line like this, one, and then the other line is in this direction. And then the tige, I'm going to draw it in green, like so. Then the unit vectors, I'm going to draw them in blue. Okay, so the unit vectors will be in blue. The reference frame that is absolute is going to be in red. Then the moving frame is going to be in black. Okay, so then let me indicate the unit vectors in blue. So for the reference frame that is fixed, we have the Cartesian coordinate system here. So we have the vectors jk, I, jk. Okay, so along the y-axis we have the vector j. Along the y-axis we have j. So along the y-axis we have j. Along the x-axis we have I. Along the z-axis we have the vector k, the unit vector k. Okay, and then this is the z-axis. So then for the reference frame that is absolute, that is moving, and for the reference frame that is moving, so here we have an angle theta, like so, and then our point M is here. So this is where our point M is, and then of course E rho is going to be in this direction. E rho is going to be in this direction. Then according to the diagram, E phi is in this direction. And then we have U2 here, and then here we have U1, like so. So we have U1, and then we have U2 there. So maybe what I can do is get rid of this and write the U2 like this. Okay, and then the origin, so we also have a line here. We also have a line. I'll draw it in black, but then the line is going to be like this. Right, so this is what we have. Then the origin of this reference frame, so we have O. So like this. So this is O. I have to change the thickness of the line. So this is O, and then this is O1, like so. Let's now read the question as we are looking at this diagram. So let me shift my screen. Yeah, so it's already, let me change my screen. So like so. So that's our question. That's the question. So let's read the question. So the question is saying, soit R, so R, O, I, G, K, un référentiel absolu muni de la base IGK et R1 with the origin O1, and then the vectors u1, u2, uk. So here we can see that we have k, k, meaning the z-axis of the reference frame that is fixed, or the reference frame that is absolute, is the same as the z-axis of the reference frame that is moving. So they have the same z-axis. They share the same z-axis. If we go back to the diagram, we can see that they share the z-axis. Okay, they share the same z-axis. That is why I've just drawn the z-axis in red here. They share the same z-axis. Okay, fine, we understand. Now let's then on done O1, O1, the vector O1 is equal to ATK. The vector O1 is equal to ATK. Okay, so this expression here, it is a distance from the origin of the reference. That is, it is a distance from the origin of the reference frame that is fixed to the origin of the reference frame that is what? The reference frame that is moving. So that is the distance. So we have that distance like so. Then we continue reading, and then OA est une constante positive et T représente le temps. En plus, R1 tourne autour de l'axe OZ avec une vitesse angulaire constante ω1 is ω1 tel que. So they are saying that the reference frame that is moving is turning around the z-axis. Is turning around the z-axis with an angular velocity of ω1, with an angular velocity of ω1 that is constant. So they are saying that this angular velocity is constant, right? So that's what they are saying here. So let's continue reading. And then dans le plan horizontal, or we can also look at the diagram that is here. Dans le plan horizontal with origin O, U1, U2, une tige T tourne autour de l'axe O1, Z. So here there's a tige in the plane U1, U2. This green part here represents the tige, where the point M, so the point M is on the tige. This point M is on the tige. So this same tige also turns in this plane, with an angular velocity of ω2. Now you don't have to confuse things here. The reference frame that is moving, the one that is in black, is turning around the z-axis with an angular velocity ω1. The tige that is in the plane U1, U2 is turning with an angular velocity of ω2. An angular velocity ω2. Okay? An angular velocity ω2, where E rho is the unit vector porté par la tige. So the unit vector along the direction here, along the tige here, is E rho. So that is what they've represented here. So remember, this is mouvement relative. So they'll be asking us to find the relative velocity, la vitesse d'entraînement, the absolute velocity, l'accélération relative, l'accélération d'entraînement, l'accélération de Coriolis, and then they'll tell us to find the absolute acceleration. So that is what the question is demanding. So let's look at how we can calculate le vector vitesse. Now, the first thing that we want to do is, before we even calculate the vector vitesse, is to know the position of this point M. How we can keep track of this position, of the position of the point M. So here we can use our knowledge of la base cylindrique to sort of like tell the position of this point, of this particle M. We can use what we know about la base cylindrique. So if you use la base cylindrique, what is the position of vector? What is the position of vector of the point M that has been, drawn the way it has been drawn? What is the position of vector? So that's the first thing that we want to do. So let's go back to the board and see how best we can answer this question. So we want to find the relative velocity, like so. So with this diagram, I want to find the relative velocity. So the black reference frame is turning around the z-axis with an angular velocity ω1. The tige is also turning, but with an angular velocity ω2. Then this reference frame that is moving is doing two kinds of movement. It is doing some translation here. We can see that the origin has moved from O to O1. It's also rotating. So two kinds of movement we have here. So to be able to calculate the relative velocity, meaning the velocity in this reference frame that is moving, that's the relative velocity. The relative velocity is the velocity of the point M in the reference frame that is moving. So let's calculate first of all the position of the point M. Now we can, because we have an angle theta here, we can make use of la base cylindrique. We know that OM, O1M, because we're supposed to find the relative velocity, O1M is going to be equal to what? It's going to be equal to this distance here. They are calling it rho according to the question. So let's go back to the question and maybe see what I'm talking about. So if we go back to the question, you see that they've given us OM. They've given us here O1M is given by this expression that we have here. So they've already given us the position vector, but here you can also look at the diagram and deduce the position vector. Okay, so you can also find the position vector, the one they've given us here, by just looking at the diagram. Okay, so that is where we're going to get the information from. Okay, right. So we know that O is rho, E rho, like so. Let's now calculate the velocity, the relative velocity. So it is the velocity in the reference frame that is moving. The velocity in the reference frame that is moving. So to be able to find the velocity, the relative velocity of the point M in R1, so we're going to, let us call the reference frame that is absolute, we're going to call it R. Then the reference frame that is moving, we're going to call it R1, like so. So we are saying we're going to call it R1. Let me use red R for the reference frame that is fixed, and then black, another color, for the reference frame that is moving. So to find the relative velocity, we must first of all, by definition, find the derivative of the position vector. So it is the derivative with respect to time of O1M, like so. So meaning we're supposed to differentiate with respect to time, rho, E rho, like so. Or what we're supposed to do here is to apply the product rule. Now you can see here that rho is not constant. Rho is not constant. Rho is not constant, and then E rho is also not constant. Okay, rho is not constant. E rho is not constant. Why am I saying this? So rho is this distance here. If you use the la base cylindrique, we're talking about this distance. The point M is moving on this tige. So if the point M is here, if the point M is somewhere here, you can see that the distance from the origin is different than when, if the point is going to be here. If the point is going to be here, then the distance from the origin is still different. If the point is where I've drawn it, then the distance from the origin is also going to be different. So rho is not the same. Even E rho is not the same, because this reference frame is turning. So when it turns such that maybe we have this axis here is somewhere here, and this one is somewhere here, you see that we won't have the same vectors, E rho and E phi. So they will change. So meaning they are not constant. However, we have to apply the product rule here. So we'll first of all differentiate the first vector and leave the second one alone. So dt, we differentiate the first vector and leave the second one alone. So if I differentiate the first vector, I'm going to have rho point, like so. If I leave the second one alone, I'm going to have E rho. Now here you have to be very careful. You have to remember what we've been doing. We said you cannot directly differentiate E rho with respect to t, because E rho depends on the angle phi. So you first of all have to plus. So here I'm going to say plus. So here we leave rho alone, and then we differentiate we differentiate E rho. So maybe if this is not clear, let me just write it in a better way. So here it is rho E rho, like so. So the derivative of E rho with respect to time, let me remind you one more time, with respect to time, the derivative of E rho is going to be equal to what? Is going to be equal to the derivative with respect to phi of E rho, and then multiplied by the derivative of phi with respect to time. So we've not changed anything here. So this is what we have. Okay. So if you differentiate E rho with respect to phi, you're going to get E phi. But this one with respect to time, dphi with respect to time, you're going to get phi point, and then this is going to be e phi, like so. So this is what you get. Okay, this is what you get. So this is the relative velocity. This is the relative velocity. Now let's calculate the second question is saying calculer la vitesse d'entraînement, which is VE. So it is very easy to calculate VE. C'est très facile. So how are we supposed to calculate VE? We just apply the formula. Now, even though we've not derived this formula, we are still, calculating. We are still, we are still trying to derive the formula for vitesse relative. That's why we ended yesterday. We can just, know the formula and apply it. Okay, we can just know the formula now and apply it. Then we'll derive it when we have, the next lesson or the next session. So, la vitesse d'entraînement, so VE, like so, of the point M is, so by definition, this is the velocity of this moving frame, the velocity of this moving frame with respect to what? With respect to the frame that is fixed. That is what the vitesse d'entraînement is going to represent. The movement of this reference frame with respect to the reference frame that is fixed. So the movement of the reference frame that is moving with respect to the reference frame that is what? With respect to the reference frame that is not moving. So this is going to be equal to, it is the derivative of this vector O1. So this represents the translation. The rate at which the rate at which the reference frame in black, the one that is moving, the rate at which it is translating. That's what the first parameter is representing. The first parameter is representing the rate at which the reference frame that is mobile, the rate at which it is traveling with respect to, the rate at which it is translating with respect to the origin or with respect to the reference frame that is fixed. So that is what the first parameter is about. The second one is about how this reference frame that is moving, the rate at which it is rotating with respect to what? With respect to the frame that is fixed. So the other term is going to be gamma of R1 par rapport à R2 and then vectoriel O1M, like so. So this is the relative position. So this is the relative position. So this is the formula. So let's apply the formula now. So this is, we've been given O1, and then we've been given the angular velocity of the reference frame R1. So here it's not R2 but R, sorry. We've been given the angular velocity. We've been given the angular velocity of the reference frame R1 with respect to R2. It's omega. Then they've also given us this distance O1 in the question. If you read the question, you find the distance. They've given us the distance. So this is going to be D. It's going to be AT along the K axis, because along the Z axis. Because if you look at the way this reference frame, the one in black, the way it's translating along the Z axis. So it's along the Z axis, the position. So if I take the derivative of this, that is going to give me the rate at which the reference frame that is moving, the rate at which it is translating. It's translating along the Z axis. So dt, like so, and then plus, then the angular velocity they've given us, vitesse angulaire, they've given us of this reference frame that is mobile with respect to the one that is fixed. Okay. So I think I wrote R2 again here, but it's supposed to be R, like so. So par rapport à R, like so. So plus, we've been given it's omega 1. Omega 1, it's turning, if you read the question, they are saying it's turning around the Z axis. It's turning autour de l'axe Z. And so here we'll put our K, like so. And then vectorial, what is the position, what is the relative position? The relative position they've also given us in the question, it is rho, E rho, like so. So this is very easy to calculate. If you differentiate this one with respect to T, you have A, like so. Then K is fixed. K is fixed. So the derivative of k is going to be what? Is going to be 0. So the final answer here is going to be ak. You have to apply the product rule again here when you differentiate, because we have a product of 3 items. So a, t, and k. So the first part you differentiate a, then you leave the others the way they are. You then differentiate t, you leave the others the way they are. You come and differentiate k, then you leave the others the way they are. So when you differentiate k, you get 0. So verify that after you differentiate here, you get a k, like so. And then plus, here you can multiply the constants using normal multiplication. When you have a vector product and you have constants that are accompanying the vectors, what you can do is that you can multiply the scalars using normal multiplication. So you have omega 1 multiplied by p, and then take the vector product of the remaining vectors, or of the remaining unit vectors in this particular case. So it is going to be k vectoriel e rho, like so. Now remember that we have a trièdre direct. So what does that mean? It means that if I'm taking the vector product and I'm going in this direction, e rho, e phi, ez, like so. If I take the vector product between these two vectors, it is going to be this remaining unit vector, but then positive of this vector, because I'm going in this positive direction. So I have to respect this direction. So it's like we are in a circle. If I draw it in this, if I draw it the way I've drawn it, you see that when you come and say, you'll be confused when you take the vector product between ez and ex. So let me draw a circle. It's like we are moving in a circular path. Then the positive sense of rotating, or the positive sense of moving, is the one that I've indicated here. So this is your e rho, and then your e phi is here, and then your k is here. Okay. So if you say e rho vectoriel, you can write k here, or you can write ez. C'est la même chose. So if you say e rho vectoriel e phi, you're going to get k. If you say e phi vectoriel k, you're going to get e rho. If you say k vectoriel e rho, you get positive this quantity. Okay, this is what we have. K vectoriel e rho is going to be e phi. So you're going to get a k, and then plus omega 1 rho, and then e phi, like so. So this is your relative velocity. The next question is saying find the absolute velocity. Now this one is très facile. The absolute velocity is going to be equal to la vitesse relative du point M in R1, and then plus la vitesse d'entraînement. Okay, the one that we've calculated. Okay, and so this is going to give us, if you just have to, you already have the vitesse d'entraînement, you get this expression, you plug it here. Then la vitesse relative, we found this expression here. So you get this expression and inject it here, and then you find the sum. Then you factor out the common terms and simplify. Then the final answer you get for the relative velocity, for the absolute velocity, the final answer is going to be, the final answer for the absolute velocity, if you factorize the common terms, factor out the common terms and regroup the terms, you get rho point, and then e rho, like so, and then plus rho, and then omega 2, and then e phi, like so, and then plus a k, like so, and then plus omega 1 rho, and then e phi, like so. So this is what you're supposed to get. So verify. It's very easy. You already have the two expressions, vitesse relative, vitesse d'entraînement. So you can calculate the sum of those two expressions. You regroup the terms and then factor out the common terms and then simplify. You will be able to get your answer. Bien. Let's look at what the other question is saying. Let's go back to the browser. Let's see what the other question is saying. The fourth question is saying déterminer le vecteur accélération relative déterminer le vecteur accélération relative. Now this one is also easy, because if you want to find the relative acceleration, all you have to do is to find the derivative of the, all you have to do is to find the derivative of what? All you have to do is to find the derivative of the relative velocity. We are just supposed to find the derivative of the relative velocity. So what is the relative velocity? The relative velocity, we already have the expression for the relative velocity. So this one is also an easy question. So let's find the relative velocity of the point M in R. So this is going to be equal to the derivative of the relative velocity M, like so, and then dt with respect to R1. It's with respect to R1 because we're talking about relative. So it's in the reference frame that is moving, the one that is black. So the derivative of what item? The derivative of rho point, and then e rho, and then plus rho, and then phi point, and then e phi, like so. Okay. So this is what we have. So remember that this operation of for differentiation or for finding the derivative is distributive. So here we can distribute it and get dt. So I can say rho point, and then we have e rho, and then plus the derivative with respect to time of rho point, and then phi. Sorry, it's rho and then phi point, rho and then phi point, and then e phi. So we already looked at how to apply the product rule on three vectors. So I will leave it to you guys to sort of like verify and verify the final answer. Okay. So the final answer here is going to be, it's easy. That's why I'm leaving it to you to to sort of like go through it. So here you're going to have rho point like so, minus rho and then phi point squared, and then e rho, you're going to easily find the derivative here, and then plus 2, and then rho point, like so, and then phi point, and then plus rho, and then phi point, like so, and then e phi, like so. So this is the absolute, the relative velocity, sorry. Then the other question is saying déterminer l'accélération d'entraînement. L'accélération d'entraînement, that's what we're supposed to find. Here again, we just have to apply the formula, even though we've not reached this far in the coup, but here we just focus on the formula. We just look at the formula, and then it's easy. It's easy to understand. So the formula is going to be l'accélération d'entraînement is going of the point M describes the acceleration of the rate at which describes the rate at which the reference frame that is moving is actually the rate at which it is at which its velocity is changing. Okay, so we have the first term is about translation. The first term is just like for relative velocity. It's about translation, describes translation, the translational movement of what? Of the reference frame that is moving. So that is with respect to the one that is fixed. Okay, so like so, and then plus again d omega. Now normally what we write here is big omega like so, of r1 with respect to r, like so, and then dt, like so, and then vectorial. So this formula is a bit long, so it's just something that you must try to remember. So plus again big omega like so, and then we have vectorial big omega, okay, and then r1 vectorial r, like so, and then vectorial omega r1 vectorial r, like so, and then vectorial o1 m, like so. So this is the whole formula. This is the whole formula. Now there's one statement that you must, first of all, as you are solving this exercise, you must always get back to the question and read the question again. So let's read the question one more time. This time we'll only focus on the parts that are talking about these, the angular velocity. We'll focus on the parts that are talking about the angular velocity. So let's look at the angular velocity of the reference frame that is turning with respect to the one that is absolute. So here we have en plus, we have R1 tourne autour de l'axe OZ avec une vitesse angulaire constante. So if you get this phrase, and then if we go back to the board like so, let's look at the formula one more time. If we look at the formula, let's examine the formula. So we have the second derivative, the second order derivative of the vector O1 plus the derivative of this rotational vector with respect to what? With respect to time. So look, they are saying that the reference frame that is moving is turning with constant what? Constant angular velocity. It means if I take the derivative of this constant angular velocity, I'm going to get what? 0. Now, if I don't have that term, I have to evaluate this expression. I have to evaluate and find the exact value. But here they are saying it is constant. The angular velocity is constant. So if I take the derivative of this angular velocity, I'm going to get 0 with respect to time because it is constant. So I'm going to get 0. So 0 vectorial, this vector that we have here is 0. So this formula simplifies to this. So this formula simplifies to this. So d squared O1 like so. And then dt squared like so par rapport à R. And then plus oméga de R1 par rapport à R. And then vectoriel oméga de R, oméga de R1, sorry, oméga de R1 par rapport à R, and then vectoriel O1 M, like so. Okay? Then let's now substitute the terms. Let's now plug in the terms. Which is also something that is easy to do. So plug in the terms. So here we are looking for the second derivative of OOM. So d squared dt squared of OOM. OOM is, according to what they've given us in the question, it is ATK, like so. It is ATK, like so. Okay, it is ATK, according to what they've given us in the question. Okay. So according to what they've given us in the question, that is the expression we have. Okay. Bien. And then plus, then this part that we have here is omega 1, because it is the angular velocity of the angular velocity of the reference frame that is turning with respect to the one that is fixed. So we have omega 1, we have omega 1 k, like so, and then vectorial, and then same thing here, we have omega 1 and then k, and then vectorial, then the relative position is rho, e rho, like so. C'est facile. So if you differentiate this for the first time with respect to t, what do you get? You get ak. Make sure you apply the product rule here so that you understand what is happening here. Make sure you apply the product rule. So you have ak. You differentiate ak with, again, because we're supposed to take the second order derivative. You differentiate ak, you get 0 because it's a constant with respect to time. So this is also going to be 0. So the final answer is going to be this evaluation. So vectorial omega 1 k, like so, and then vectorial rho, and then e rho, like so. So this is what we're going to have. Okay, this is what we're going to have. Right, let me just double check to see if there's any mistake, because this formula is very long and it's easy to make mistakes. It's easy to make mistakes. Have I left out anything? So we have d squared O1 dt squared, and then plus. Then we have this part where we're differentiating. Then we have this vectorial this, and then we have plus this omega here, and then vectorial the first one, okay, which is okay. Vectorial the first one, which is okay, right? So this is what we have. This is what we have. Okay. So right. So we have, let's first of all take the vector product of what is inside. If you want here, you can apply double produit vectoriel. Here we have a double produit vectoriel. So what we can do, we can apply the formula for the double produit vectoriel. Hopefully you guys remember that formula. So it's, we say it is omega 1. It is the first vector. It is, now first of all, you can get the constants. To simplify things here, you can multiply the constants using normal multiplication. So if you multiply the constants using normal multiplication, you get omega 1 squared. You get rho omega 1 squared if you multiply the scalars using normal multiplication. And then you'll be left with k vectorial e rho, like so. This is what you'll be left with. And then we can now apply the double produit vectoriel inside. So, like so. So if you apply the double produit vectoriel here inside, the formula for the double produit vectoriel, it is, you write the first vector outside, like so, and then you take the dot product, and then you take the dot product of, and then you take the dot product of, so it is the first vector, take the dot product of the, you take the dot product of the other two vectors that will be remaining. So that is the double produit vectoriel. If you apply the expression for double produit vectoriel, so you have k, and then you have k dot e rho, like so, okay, and then minus let's see. So rho omega squared, like so. So k vectorial k vectorial e rho, like so. Let me just verify the formula for the double produit vectoriel. Double produit vectoriel. Double produit vectoriel. Double produit vectoriel. Double produit vectoriel, bien. Right, so we have the double produit vectoriel. So I've made here, just like I said, you have the scalars, you can deal with them, and then you can remain with the vectors. And then you're going to have k, yes, vectoriel, again k, vectoriel, and then e rho, like so. So this is what you're going to have. K vectoriel, e rho. This is what you're going to have. So what you do is, it is now the first vector and the third one. The first vector and the third one, we take the dot product. So we take the dot product of the first vector and the third one, which is e rho, and then the second one will be out, like this. And then minus, then we'll come and take the dot product. We'll come and take the dot product of the first and the second, okay? The first and the second. So it is k, like so. And then the other one is going to come outside, like so. Oh, what do we know? We know that when we're taking the dot product and then the vectors are perpendicular, because k and e rho are perpendicular, this is going to be 0. The dot product of k and k is 1. So finally, we should have minus rho omega 1 squared e rho. So this is going to be the final answer. Okay? That is le double produit vectoriel. So that's our final answer. Minus rho omega 1 squared e rho. C'est très facile. So let me just apply it here. I've applied double produit vectoriel. Double produit vectoriel is what you're supposed to apply here. Produit vectoriel. Okay. Right. So let's look at the other exercise. For the other, we've calculated l'accélération d'entraînement. So the other question is to find the accélération de Coriolis. Accélération de Coriolis. That's what we're supposed to do. So again here, we just apply the formula. We just apply the formula here. L'accélération de Coriolis is going to be equal to 2 times the, now let me just use big omega, 2 times the angular velocity of r1 with respect to r, and then vectoriel the relative velocity. So I'm going to leave this one to you. The final answer here is going to be 2 omega 1. Verify. This is easy because you just have to apply the vector product and use the techniques that I've shown you to apply the vector product. So I have 2 rho omega 1 omega 2, then e rho, like so. So this is the final answer. And then the last one is about finding the absolute velocity. Well, absolute velocity, absolute acceleration. Absolute acceleration is going to be the sum of the 3 accelerations that we found. Okay, the sum of the 3 accelerations that we found. So the first one that we found is l'accélération relative, and then plus l'accélération d'entraînement, and then plus l'accélération de Coriolis, like so. Then just add all the 3 expressions, group the terms, and then factor out the common terms, then simplify. You'll be able to get the final answer. So I'm going to leave it here. Now there's one thing that I want to tell you about, these calculations. Since you found the absolute velocity, right? I know you'll be tempted to, when you're asked to find the accélération absolue, when you're asked to find the absolute acceleration, I know you'll be tempted to find the derivative of the absolute velocity. No, don't do that. Do not attempt to find the derivative of the absolute velocity. Just apply the formula. Always apply the formula. Find the accélération d'entraînement, find accélération de Coriolis, and then find accélération relative, and then add the terms. Okay, don't attempt to take the derivative of vitesse absolue so as to find accélération absolue. Don't attempt to do that. Okay, don't attempt to do that. So that is all for the 2 exercises, and I'll see you next time.